Hello everyone, this is Doug, and in this video we're going to continue our discussion about the ideal gas law, about PV equals nRT. And we're going to take a look at it, sort of different types of questions that you can use the ideal gas law to figure out. So let's get to it. Remember that the ideal gas law was this best friend of ours, PV equals nRT. We talked about how P equals the pressure, V equals the volume, N equals the number of moles. R is just a gas law constant. It's one of these. This is just a list of 5. There's many more depending on how you change the units. But again, I'm just using this one, the 0.0821. I usually just go to 1 or 06 because I like to get everything back into atmospheres and Kelvin and liters because they're very common units. And then T, of course, is temperature, and that's in Kelvin. So we're going to use this ideal gas law to figure out a whole bunch of different things about gases. Now, in the previous video, right, I showed you how to do this. I did the missing variable thing already. That was in the previous video. In this video, what we're going to do is we're going to take a look at what happens if you have just a certain amount of gas, the same number of moles, and you change stuff about it. You change the temperature. How's that going to affect the pressure? Or you change the volume. How might that affect the temperature? And so on, right? So a type of question might be something like this, where you say, a gas is at standard temperature and pressure in a rigid 5-liter container. The temperature is increased to 100 degrees. What's the new pressure going to be, right? And so we're going to use this derivation of the ideal gas law, and I'll show you how to derive that in just a sec. And then the next video, we will talk about using these gas laws in chemical equations. So how did I derive that P1 V1 divided by T1 equals P2 V2 divided by T2 equation? Let's kind of talk through it here. What we're saying is that we've got a gas before and after a change. So I'm going to do the ideal gas law, so just P1, like this initial value, V1 equals N1. R is just constant always, so I don't have to say, give it a subscript 1 or anything like that. RT, 1. And again, I'm saying 1 because that's just supposed to be like the before times. So right before, this would be the gas at standard temperature and pressure in a 5-liter container. And then I'm also going to write the gas law over here, P2 V2 equals N2 R and T2, right? So afterwards. So now what's the ideal gas law once we get to 100 degrees? And what I want you to notice here is that when I'm looking at this, right, since this is the same gas, what I know is that N1, the number of moles that I start with, is still going to be the same number of moles I end with. So N1 and N2 are equal to one another. Also, the gas law constant, right, it's a constant. It's going to be the same also. So really, for both of these, the N and the R are going to equal each other. So what I can do here is I can take my two formulas and I can isolate the N and the R. So on this one, I'll divide by T1. So that I get N1 and R equals P1 V1 over T1. And I'll do the same thing over here on the right where I'll isolate my N and my R. So I'll divide everything by T2 so that I get N2 and R equals P2 V2 T2. But remember, I was just saying here that that the number of moles and the gas law constant before and the number of moles and the gas law constant after are going to be the same as one another. So what I can do is that I can just set these equal to one another so that they cancel out and then get my new equation here, which is just saying that the pressure times the volume divided by the temperature when you start is going to equal the pressure times the volume divided by the temperature when you end, right? So that was that equation that I was talking about, this one, right? That P1 V1 divided by T1 equals P2 V2 divided by T2, right? So we're able to take two of the ideal gas laws before and after and combine them because if it's the same number of moles of gas, we can just set those two equations to equal one another, which is just like your basic algebraic manipulation. So hopefully that seems kind of familiar, but that's how you would derive this. So I'm going to use this as a starting point, what I have down here in green and purple. I'm going to use this as my starting point for all of the questions that involve a gas changing states, right? A before and an after, right? So I have my 1s and my 2s. So let's apply that to this question. So I've got my P1, all right, here's my equation right here. Just write it out for you. What we're saying is that we have a gas at standard temperature and pressure. And remember, I know that that means, right, standard temperature and pressure equals 1 atmosphere, and it equals 273.15 Kelvin. Oh, sorry, that's, yeah. Yep. And what we're saying here, here's what I always like to do with these equations. It looks like it's saying that the temperature increases to 100, and it's asking the new pressure. And so what I want to do every time is figure out which of these three variables is not going to change, right? So that's going to ask myself first, which variable is not changing. And what I'm going to do is I'm going to cancel it out. Right? So if I look at this question, it says that it's in a rigid 5-liter container. It's rigid. It's not going to change the volume, right? If it's rigid, it's not going to, think of like a metal box, right? A metal box isn't going to change its volume depending on the pressure that it's in, right? It's going to stay the same shape. It's not like a balloon that has a very, whose volume can change super easily. So if I see this, it looks to me like the volume is not changing. So that means the volume before and the volume after are going to be the same. So I can just cancel those out. So I'm going to rewrite my equation as simply being P1 over T1 equals P2 over T2. I'm going to look at just the things that really are changing or that I'm being asked about. And so the pressure that I'm starting with, I know is just 1 atmosphere, right? Because we're starting at STP, which is 1 atmosphere. I also know the temperature that I'm starting at because it says it's at STP, so 273.15 Kelvin. And I'm looking for what is the new pressure. So I'm trying to find P2, and it's saying that the new temperature is 100 degrees Celsius, right? And remember that if one temperature is in Kelvin, I need to have them both in Kelvin, or if one's in Celsius, I need to have them both in Celsius. And so I'm going to go ahead and take my 100 degrees Celsius, add my 273.15 to get my 373 Kelvin, and for sig figs, I'm dropping the 1.5, so 373 Kelvin. And then I just solve for P. So in order to solve for P, I'm going to multiply both sides by 373 Kelvin. Sorry, I ran out of space, times 373 Kelvin, so that I can solve for P2. So I'm going to take 373 Kelvin times 1 atmosphere divided by 273.15 Kelvin to get my P. And if I do that, I get about 1.25 atmospheres. Let me include my unit here. 1.25 atmospheres. And if you've played with that simulator or you've looked over like Charles' law, Boyle's law, Avogadro's law, right, just in general, it makes sense then if I have a sealed container and I increase the temperature, my pressure should go up. It went from 1 atmosphere to 1.25 atmosphere. So raising the temperature always raises the pressure if everything else is equal, which is what we see here. So that makes that value makes sense. You can kind of double check your work by thinking logically about it, right? So I have a sealed container, I increase the temperature. That means the gas particles are moving around faster. They're gonna have harder collisions, and therefore the pressure goes up, which is what we see. So let's try this on another type of problem. So let's look at a new problem here, right? This question says a balloon has a volume of 576 milliliters at 22.3 degrees Celsius. Assuming that the pressure is constant, what will be the volume of the balloon at 0.05 degrees Celsius? So this is another question where I'm changing a parameter, I'm changing a property of a gas, so I know I'm doing that sort of modified ideal gas law. So I know I'm going to do something with this P1 V1 T1 equals P2 V2 T2. And again, like with the last one, I'm going to look for what is constant here. I can usually get rid of one of these variables, either the pressure, the volume, or the temperature. This question says the pressure is constant, so that means that these are the same. So I can get rid of that. And that means I can turn my equation here, I can simplify it into just V1 over T1 equals V2 over T2. So I just need to find my volumes and my temperatures. For my volume, it looks like I have 576 milliliters. Remember that the R that you're using has a set amount. And so I like to just change everything back into liters, change everything back into Kelvin so that I know that the R value works for these, even though the R isn't really seen here. Volume you can kind of get away with. Celsius or Kelvin. Celsius for Kelvin you can't. You got to convert back into Kelvin. So I'm going to go ahead and change my 576 milliliters into liters. Doing a good old conversion factor, so 0.576 milliliters. That's what's going to be in my numerator here, so 0.576 milliliters. For my T1, it says it's at 22.3 degrees Celsius, so I got to convert that into Kelvin, so 22.3 degrees Celsius plus 273.15 Kelvin, or I guess not really Kelvin, that's just the modifier, is going to equal 295.5 Kelvin. So that'll be my initial temperature. And that's going to equal, what am I looking for? The volume. I'm looking for the volume. And the final temperature here, the final temperature is 0.05 degrees Celsius. So I got to convert that into Kelvin also. And that is going to be 273.20 Kelvin. And that's my final temperature. And then I do my normal math here where I'm going to multiply by the 273 to get it out of that numerator so I can isolate my V2. So sorry for the sloppiness. I'm running out of time here. 273 point, not time, space, and time. So I'm going to multiply each side by that. Let me write that a little bit neater. And so when I do that, right, those cancel. I solve for V2 by taking 273.2 times 0.576 divided by 295.5. And that's going to give us, in liters, 0.532 liters. So it looks like if the pressure is constant and I lower the temperature, the volume decreases, which also makes sense given what we know about gases, right? And I think I mentioned before, right, if you take a balloon and you put it on ice, it's going to start shrinking on you, right? If you lower the temperature, the gas particles don't move as quickly, so they don't bounce against the container as much, so their pressure goes down, which makes the volume go down. And so let's try another one of these. Here's a question. A piston compresses a gas at standard temperature and pressure from 0.662 liters to 0.100 liters, right? So we are decreasing the volume. Assuming that the temperature does not change, what is the new pressure of the gas? So again, P1, V1, T1 equals P2, V2, T2, right? Because I'm seeing a change in a property of a gas. I'm going to ask myself, well, what is staying constant? It says that temperature does not change. So I'm going to take these temperatures and get rid of those. So that means my new simplified formula that I'm going to use is just P1, V1 equals P2, V2. And then I just need to plug stuff in. So my pressure to start off with, since I'm at STP, I know my pressure is just 1 atmosphere. My volume apparently is 0.662 liters. The pressure afterwards is what we're being asked about, and my volume afterwards is 0.100 liter. To get that isolated, 0.100 liters, divide both sides by that, so that I can isolate my P2. And if I solve for P2 here, I see that I get 6.62 atmospheres. That's going to be my new pressure. And again, if I look at that, right, so I'm taking this and I'm compressing the gas, I should see temperature goes up. sorry, not temperature goes up. The pressure goes up, right? If you take something and you compress it, you're increasing the pressure on something. So it should be 6.62 atmospheres. So let's do one. Here's one about a scuba tank. A scuba tank has a volume of 2 liters. Actually, I guess it doesn't matter. It doesn't matter. 2 liters. Let's say it's 2 liters. It's more like 11 liters, but let's just go with it. A scuba tank has a volume of 2 liters, and the pressure gauge reads 2,111 psi at room temperature, which is about 25 degrees Celsius. If the gas was released from the scuba tank, what volume would that gas occupy at 1 atmosphere, at normal atmospheric conditions? And we're just going to assume that temperature does not change. So I want you to pause, for real, set up your P1 V1 divided by T1 equals P2 V2 divided by T2, eliminate one of those 3 variables based on the question, and solve for those. So go ahead and pause and take a crack at that. So I've got my P1, my V1, T1 equals P2 V2 T2. If I look at my question, it says just assume the temperature does not change. So again, I'm going to get rid of these suckers, which means that my equation becomes simply P1 V1 equals P2 V2. And then I just need to start putting in my values, right? So I've got 2,111 PSI, but I'm going to convert that back to atmosphere, especially since they talk about atmosphere in the other one. I'm just going to convert to atmosphere. So you just look up this value, right? So apparently the conversion factor for PSI to atmosphere, PSI to atmospheres is just 14.7. And if you solve that, you're going to get 144 atmospheres. The volume that it started at was 2 liters, 2.0 liters. It just said that in the question up here. And what's that going to equal? Well, the pressure afterwards, it says, is 1.00 atmospheres. Right, that's from up here in the question. But we don't know the volume afterwards. We don't know the V2. So I'm going to divide each side by 1 atmosphere. So I can get rid of that from this. And then if I do that multiplication and division, I get that my V2, my new volume, is going to equal, let's see, 288 liters. 288 liters. So that's how we do these sorts of problems, right? So if you have a gas, the number of moles doesn't change, you're going to have this sort of combined gas law thing where you have the before and after equal one another. Just find which variable is remaining constant, get rid of it, plug in everything else, and solve for the thing that you're looking for. So we've done 2 types of ideal gas law problems now. In the next video, we'll talk about using ideal gas law in chemical equations, so you're reacting things, you're doing stoichiometry. So keep an eye out for that. Study up. Good luck.